hear me? Hello? Am I audible? Okay, thank you. So, hi, I'm Rohit Kumar Singh, the teaching assistant for this course, Wave Optics. And this course is being taught by Professor Samudra Roy from IIT Kharagpur over NPTEL portal. And this is the third live session. So in the last Saturday, basically we recapped some concepts of superpositions of waves and what is group velocity, phase velocity, and things like that. And we solved some problems based on them. So today, going further, we will recap some concepts of interference. So basically, superposition of waves leads to interference and diffraction. So we will see how we can understand that, and then we'll solve some problems based on them, examples. So is that okay? Do you have any question before we start? Okay, thank you. Okay, so then let's start. So yeah, so last time we saw that if we have two sinusoidal waves like x1 and x2 given by a2 cos omega t plus phi 2, so with amplitude a1 and a2, we saw that when these two waves will superpose, the resultant amplitude of the wave will be given by this formula. So it will be basically a1 square plus a2 square plus 2a1 a2 cos theta 1 minus theta 2, right? 1 over square root of this quantity. And similarly, the phase difference, the resultant phase, basically tan of the resultant phase is given by a1 sin theta 1 plus a2 sin theta 2 and a1 cos theta 1 plus a2 cos theta 2. Okay, so this we derived last time, and what we can see here is that if this difference of angles theta 1 minus theta 2, so sorry, this is theta not phi, yeah, if this difference is equal to 0, 2 pi, 4 pi, we see that the amplitude is gets added up, right? And this we called constructive interference. And when this phase difference is odd, odd multiple of pi, so pi, 3 pi, 5 pi, such things like that, then the amplitude is like subtracted, right? And we have destructive interference. So one question can come to your mind that if these two amplitudes are equal, then what will happen is that for this case you will get a equal to 2a, and in the second case you will get a equal to 0. So you will see that there will be a pattern that at some point you will have a bright more brighter light, or at some places you will have darker light. So this is the concept of interference basically. So the two waves are interfering such that they are producing bright and dark light. So so this is a very interesting thing. So light plus light makes something dark, right? That is what is happening here. So, and this was not expected uh, earlier, because people thought that light is a ray. I mean, light is made up of particles. It's not a wave. So this can never happen. But after this Young's double slit experiment that you all familiar with, this wave theory of light came into picture. Okay. So yeah. So let's recap. The double slit experiment, basically Young's double slit experiment. So, let me write it. I will not go into much detail. I'll just briefly recap. So this is called YDAC famously. So what Thomas Young did was, basically he took a source of light, okay, and made two very small openings on a cardboard. Okay, so and what happened is, the light, when light passed through these 2 points, so like this and from here, right, and then he kept a screen at a very far distance, say D, okay. Then these 2 openings, let's call them S1 and S2, okay. So what he observed is that on this screen L bar, okay, he saw this pattern of light and dark patterns, so basically fringes, okay. So that was a very remarkable discovery. So because see, light is passing here from 2 different openings, and it is creating a pattern of bright and dark fringes, and no one can understand at that time that what is happening there, okay. And this phenomena can only be explained if we consider light to be a wave. So like water, when you throw a stone in water, it creates a wave. So similarly, when from these 2 opening, wavelets emerge, and they interfere with each other, and they either constructively, at some places they interfere constructively, at some places they interfere destructively, and that produces the bright and dark fringes, right? Okay, so yeah, that is what he observed. But then how to quantify this, and how can we how can we get the condition that at which place you will observe the bright fringe or dark fringe, okay. So suppose, let's pick a point P at the screen, which is a distance x away. So let's give it an index, so let's call it xn, because there will be many such fringes, so let's call it n, okay. What happens is that at point P there will be light ray coming from this opening, and one light ray coming from this another opening, right? Now we know that just like we discussed right now, that if the phase difference between 2 light reaching there is a even integral of pi including 0, then you will have a constructive interference, right? And this you can translate into path difference. So we know that uh, phase difference and path difference is related by 2 pi by lambda, right? So let's call this distance S2p minus S1p, okay? And if these two, if this difference is integral of lambda, so n equal to 0, 1, 2, 3, like that, okay, then we have maxima or constructive interference, okay, and you get a bright fringe, okay. And now how can we relate this in terms of xn, this point, like at which point you will have maxima or minima. So to do that you can calculate this path difference basically. So to do that let's calculate the square of the differences. So S2p square minus S1p square. Now S1p and S2p, what is you can use the Pythagoras theorem, and S1p is basically d, so d square plus xn minus sorry, I am calculating wait S1p, yeah, so xn minus d by 2 whole square, right? And then S2p square is d square plus xn plus d by 2 whole square. So this distance is basically a small d, the distance between the holes, okay. Is this fine with everyone? Everyone understand this, or should I explain it? Yeah, this is class 11th 12th stuff. So okay, let's put that here. D square plus xn plus d by 2 square minus d square plus xn minus d by 2 square. Okay, if you calculate, if you do the algebra, you will find this is equal to this 2xn d. So now what condition do we have now is okay, but this is the square, I mean difference of the squares, but you can write it like S2p minus S1p S2p minus S1p will be equal to 2xnd divided by S2p plus S1p, right? Now this we can write approximately equal to x and d by d. Now how did we write this? So here we are assuming that this distance from the slits and the screen is greater than the distance between the slits, so small d, and also the point where we are observing the fringes, okay. If this condition is satisfied, then we can approximately write S1p plus S2p equal to 2d, okay. You can see from this above expressions. So basically we are saying this goes to 0, this goes to 0. So S1p is just D, S2p is just D. Okay. If this condition is satisfied, this we can write, and that we have substituted here, and we got this condition. Okay. Now, so this is what we got for the path length, and then we can write simply using this from this formula. What we get is xn is equal to n lambda d by d. So these are the maxima points on the screen. Distance from this O center. This is the maxima points on screen, right? Is everyone okay here till here? Do you need me to explain anything? So if you are not satisfied with this, you can assume, so I'll give you some examples. So if you consider the distance between the two slits, let's say 0.02 centimeter, and the distance between the screen and the slits is 50 centimeter, something like that, and the distance where we are observing the pattern, let's say it's 0.5 centimeter. Okay, this kind of numbers is easily achievable in experiments, and this will satisfy this criteria, right? So we are talking about these kind of numbers. Okay, so that's why you have to keep this screen far away from the slits to observe this interference. Interference pattern will always be there, but yeah, in order to observe them at these points exactly. So this is an approximate result, not a accurate. It is accurate up to a certain precision. Now from here you can find the width of the fringe. So what is the distance between one dark fringes, one dark and the other dark, or one bright to the other bright fringe? Okay, so basically the fringe width, and that you can calculate. So you just basically calculate the n plus 1th and nth distance, and you subtract that, and you will get lambda d by d, and this is called the fringe width. Okay, so yeah, this is about the Young's double slit experiment. Now why this simple experiment is very effective is that you see in this formula what are the quantities that you can see. You have the fringe width beta, you have the distance from the slit and the screen d, and you have the distance between two slits, and then you have this lambda, which is the wavelength of the light used. So this is basically saying that doing this experiment you can calculate the wavelength of the light, right? Because these things are measurable. You can measure the fringe width, so fringes will be like this, right? You can take a micrometer and measure this distance, that will be your fringe width. You can measure this distance, you can measure this distance, and through those measurements you can calculate the wavelength of the light. So this simple setup allows you to calculate the wavelength of the light that you are using. So that's
Hello, sir. Am I audible?
yeah, hi.
Sir, you have said that capital D should be very, very large and small d, right?
Yeah.
So, like, if it is not like that, then what happens is like, is this
Yeah.
experiment means like, if d is not so much greater than small d, then interference does not happen.
No,
Is
no, no,
it
no,
like
no.
that or
Interference
something else?
always happens. This formula won't apply. This formula this formula will not be accurate. That's what I'm saying. So then you will
So
have to.
means like Young's double slit experiment explains this phenomenon, this phenomena only set of
No, no, no. That is not a
means
problem.
like
See, this is a simplified formula. Anyways, this is S2P, S1P. You can calculate anyway, right? If you can calculate it exactly, then that is not an issue. You can just calculate it exactly, and you put this condition. You can get the wavelength of light. So everything is here is calculable, right? Is just this expression that we have derived just for the simplification of calculations. That's all. In experiment, you can do everything. You can put the screen
oh yeah.
closer also, and you can do the experiment. Then you will have to find the exact distance S1P, S2P. That is fine. That you can do, right?
Yeah, okay, sir.
Yeah. But this exact formula is applicable when this criteria is met. To simplify things, we have done this. Okay. Now, so this is the Young double slit experiment, and okay, so it has very it it has its limitations. So basically, uh, I mean, if you want to do it in your home, you will face many issues. For example, how you make these holes, make these slits, and I mean, it is very complicated thing to do. One easier thing to do is take a prism. Okay, so you know what is a prism, right? A prism is made up of glass in a shape of triangular shape. So basically it's 3D of a triangle. Okay, so let's say the base of the prism look like this. Okay, and you put a source of light here. So this is a source of light here. Okay, and so light rays will go like this. And what happens is that if light rays enter from air into a denser material like glass, it will bend towards the normal, right? So it will bend like this. Okay, and it will release like this, and here also it will bend like this and release like this. And so then if you will see it from here, you will see two sources of light, S2 and S1. So these are virtual sources of light. Okay, which will be always coherent because they are coming from the same source S. Okay, and you will observe a interference pattern from these two virtual sources. Okay, and you can similarly you can find the wavelength of the light using this formula. And beta you can measure, right? Beta can be, so this is just the fringe width. And this setup is called Fresnel biprism method, which is an easier setup to observe interference. Okay, so yeah, but everything is similar to Young's double slit experiment. All the formulas will be similar. Okay, so we will have some problems based on this. Okay, yeah. Now let's talk about another concept called coherence. We talked about it a little bit, but let's see it like how this can affect this interference if experiments. Okay, so we know that light is made up of electromagnetic waves which travel like this, which have expressions like this, right? So this is sinusoidal. sinusoidal waves, plane waves, and we assume that this is sinusoidal uh, from time minus infinity to infinity. Okay, so at all times this is sinusoidal, but that is not the case in real life, right? You cannot have a source of light which can produce perfect sinusoidal uh, wave till infinity time. So in reality, so I mean this is what we want, so perfect sinusoidal till infinity. But in reality what you have is, so after some cycle you will have some like this, and then okay. So now this time, and this is a time axis basically, okay, and this time up to which this was the wave was sinusoidal, we call it coherent time. Okay, and then you can define coherent length, which is basically L given by C times tau C. Okay, so this is the basic concept of coherence. Now in Young's double slit experiment that we discussed above, so what we saw is we had two sources of light, and suppose we are looking the interference pattern at point P from these two sources, and this distance we can call it R1, this is R2. Okay, now this the light coming reaching at P from S1 and S2 will reach at basically time. So from S1 the light will reach at time t minus R1 by C. Okay, so we are looking at time t. Okay, and from S2 it will reach at time, let's say t minus R2 by C. Okay, sorry, I mean at this time the light was emitted from S1 and S2. That's what we if we are looking at time. So if time t is here, this is the distance, then this light was emitted at t minus R2 by C, and this one is t minus R1 by C. Okay, now the condition is that if R2 minus R1 by C, which is just delta t, right, the time difference between these two times, is less than the coherent time of this light source that we are using, we can say this is a good I mean it is the light you will have basically good constructive or destructive interference, good contrast you can observe of the fringes, good contrast. Okay, and if this criteria is not satisfied, like if this is if this time is greater than the coherence time, then no fixed phase relationship will be there. So your fringe pattern will be washed away. Okay, so this is the concept of coherence. So that's why you need coherence. So if even if you are using the same source of light, it can have temporal incoherence. Okay, after some time it might go out of phase. uh, okay, so yeah, that is all I wanted to discuss. Now let's go to some problems. Okay, we'll solve some problems based on what we have discussed. Okay, so first one. So this is a problem, simple problem based on the Young's double slit experiment. So what the problem says is, okay, by the way, let me ask, everyone is fine till here, right? Do you have any question on what we discussed? Okay, thank you. Okay, then let's move. So, okay, the question says, in Young's double slit experiment setup, the fringe width is given by beta naught. Okay, so fringe width is given. Now the distance between the slits and the screen is doubled. Okay, so distance between the slit and the screen, d becomes 2d, and the separation between the slits is half, so d becomes d by 2. So what will be the new fringe width? Anyone? This is the simplest problem, right? 4 times. Sure. So okay, like what is beta? Beta is lambda d by t, right? So d becomes 2d, so 2 lambda d, and d becomes d by 2, so d into 2. Yeah, so it is 4 times of beta naught, right? Thank you. Yeah, this one was just a warm up. Okay, let's go to the next one. Okay, this is also one very simple problem on the application of this formula. So in Young's double slit experiment, the separation between the slits is given, so small d is given, and fringe width is given 0.6 millimeter, and the screen kept at a distance 1.4 meter from the slit, so this is also given. Okay, we need to find the wavelength of the light, which is just to use this formula, correct? So just simply multiply this. So what, let me, yeah, 72 into 10 to the power minus 2 mm square is 10 to the power minus 6 in meters, 1.4, right? 1.4 meters. So it will give you 14 into 10 to the power minus 1. So you have 72.
B option, I think.
14, oh, sorry?
B option.
D? D or B?
The second option.
Second.
Second.
Yeah. Yeah. Fine. Yeah, this is also very simple. So let's move to the next one. Okay. Now here the problem says the interference pattern obtained with two coherent light sources of intensity ratio n. Okay, so what does it mean? There are two coherent sources, S1 and S2. Okay, and intensity, you know, right? Intensity is just amplitude square, right? And so yeah, and the ratio of these two, I1 by I2, is basically n. Okay, and what we want to calculate is I max minus I mean divided by I max plus I mean. Okay, this ratio, and this ratio is also called visibility. Okay, this is defined as visibility. How would you do this? Any idea? So this is given, okay, for interference pattern, two sources of light is there and their intensity ratio is given, okay, and you have to find this quantity. So you have to find out basically I max and I mean. How would you do this?
Sir, means like we will find net interference by applying the formula. We will take I, means one intensity we will take as I and other we will take as Ni, right?
Sorry, can you repeat? I did not get it.
Means like we will find net intensity, maximum intensity formula we can apply and then we can find
Which
one
formula?
intensity.
Which formula? So okay,
Uh,
intensity is a square. That is mono. Okay.
Maybe we'll write I1 by I2 as A1 square by A2 square. Then we'll
Sorry.
find the resulting amplitude.
Can you repeat?
We'll write I1 by I2 as A1 square by A2 square.
Yeah.
Then we'll find the resultant amplitude.
That is fine.
Then for I max, we'll find the resultant amplitude as with that formula A1 square plus A2
I
square.
max is okay. I max. What is the resultant? Okay, resultant amplitude we know A1 square A2 square plus
Yes.
2A1 A2 cos theta 1 minus theta 2.
For I max, theta 1 minus theta 2 is 0. Or
Yeah,
that
this
term
one
becomes.
this one is for I max. This one is basically we assume this is basically 1. So this is 1 cos theta 1 minus cos theta 2 1. So I max will be
A1
basically
plus
A1 plus A2 whole square, right? A max, right?
Yes, sir. For A min, it will be A1 minus A2.
And I will be A1 I max will be A1 plus A2 square, and similarly I mean will be A1 minus A2 square, because for I mean we will have cos theta minus theta cos theta 1 minus cos theta 2, basically minus 1. Okay, so this we have, and from here we have A1 equal to under root n A2, right? And I max I mean you can put it here, and you can substitute in this formula. Okay, so what you will get, let me try do it. Okay, so yeah, everything I mean all the A1s will be cancelled from numerator and denominator. What will remain is the dependence on the n. Okay, so basically this I max will be A2 square plus 1. I'm writing it in terms of A2 square, and this will be A2 square root of n minus 1 to the whole square. So A2 square will be cancelled, and you will have plus 1 whole squared minus sorry n minus 1 whole square. Similarly, this 1 plus n minus 1, and you can simplify this. So the numerator will be 4 under root square root n, and the denominator will be 2n plus 1. So this is the correct answer, B. Fine. Everyone understood what we did? So for maxima, we just assumed this thing to be equal to 1, and for minima we assumed it equal to minus 1. Yeah, this was simple. Okay, now let's go to the next problem. Everyone is okay, right? Then okay, this is one problem on the Fresnel biprism. Okay, so yeah, so what this problem says is the acute angle of the biprism of refractive index. So refractive index is given, and the acute angle, that means this angle is given, I think alpha, it is 2 degree. Okay, yeah, and a slit illuminated by a monochromatic light is placed 10 centimeter from the biprism. So there is a source of light, okay, placed at 10 centimeter. So this distance is 10 centimeter. Okay, fine. If the distance between two dark fringes observed at a distance of 1 centimeter from the biprism, so screen is kept at 1 meter, and the fringe width is given. If the distance, yeah, the fringe width is given, which is 0.18 millimeter, right? Okay, so this is given. Find the wavelength of the light used. Now what are other quantities given? D is given 1 meter, okay, and we have to calculate lambda. What is missing? This small d, that is the distance between the virtual sources. This distance is missing. How can you calculate it? So, and what is given? This acute angle is given, alpha is given, right? Okay, so so it's a problem of geometry basically. Okay, so you have a triangle, this angle is given, and this is a distance, let's say wait, distance from the, yeah, this is the distance, let's call it L. Okay, yeah, this is L, and the refractive index is given 1.5. So this is the angle delta through which the light rays get deflected, and I mean, I'm not going to derive it, it is a very standard concept, and this deviation is given by this formula. Okay, this is a very standard formula. If you have studied about prisms, this is the deviation, angle of deviation. And if this so this angle will be equal to this angle, right, opposite angles. And if I mean, since we are considering very small distances, uh, this delta, I mean this will correspond to this distance S1s, right? And so similarly you have here another source S2, and so the D will be just S1s plus S2s, which is 2n minus 1 alpha. Okay. Yeah. Sorry. No. And there will be yeah. Sorry. S1s into wait. This is the L, right? Yeah. This will be there because this is the angle. So I mean we are basically doing tan delta is equal to S1s divided by no L oh no tan, no, not tan delta, we have to take sine. Yeah, we are taking sine delta, and so what will be sine delta? I'm trying to find out how this thing, sorry for messing up. I'll clarify in a minute. Okay, so this is the deviation. Okay, and from here I said that this S1 this S1s will be equal to L delta. Okay, here we are considering this angle, this deviation very less than I mean it is a very smaller number. Basically this is delta is very small, so that sine delta is equal to delta. Okay, or equal to tan delta. That's how we can calculate this. Is it fine? So you have 2L and minus 1. Yeah. Okay. So now we have everything. We can calculate lambda using our formula. Lambda is equal to beta d by d. So beta is given 0.18 mm. D we have calculated 2L. So 1.5 minus 1. Sorry. L is also given. This is 1 meter. And n minus 1.5 into alpha is 2 degrees. So we'll have to convert it into radians. So pi by 180 divided by sorry, oh, this is 10 centimeter, right? This distance L is 10 centimeter, so 10 centimeter. For centimeter we will do minus 2, 10 to the minus 2, and this is 1 meter. Okay, so if you do the calculation, you will find your answer. You have to convert this also in meters. There is no space left.
Excuse me, sir.
Sorry?
We have given the distance between two dark fringes. So shouldn't it be 0.18 by 2?
Yeah. So this is the fringe width. Between two dark fringes or between two bright fringes, the distance will be same.
So we'll take it as beta is 0.18.
Yeah. Okay. So now then, let's. Everyone is okay with this, right? So basically here the issue was we did not know the distance between the two sources S1 and S2, and that we calculated using this property of a prism where the light passing deflects through this angle, and through this deflection, assuming the assuming the deflection very small, we calculated the distance d. Okay. Okay. Now let's go to the next problem. Here, so this is another problem on double slit experiment. Here lambda is given 600 nanometer. The distance between the slits is given, and the distance between the slit and the screen is given. And now the question says, if we introduce a thin glass plate of thickness 0.10 mm, the refractive index, so its refractive index is given, the refractive index of the glass 1.5. Okay, and the question is, what is the phase difference introduced between the two beams by the plate, and how many fringe shifts does it cause on the screen? So what is happening is, we have our double slit experiment, right? In one of the so this is S1, this is S2. Okay, in front of one of the slit we have kept a glass slab like this. Okay, so now so this is now the light is now passing through it. Okay, and due to this, when we are looking at a fringe pattern on the screen at point P, what is happening is, there will be a phase shift, because the path length that the light will travel inside the glass will be different to what it would have traveled inside the air, right? So due to that, there will be a path difference which leads to a phase difference, and that will shift the fringes, okay, on the screen. So we will calculate how many fringes will shift. Okay, so yeah, everyone know how this problem is can be solved. I think this is the easy one, right? But anyway, let's do it. So yeah, the path difference will be delta x. So now the light will travel a path given by ng times t, right? And earlier it was traveling only t. So this is the difference of the path length, and which we can calculate. So this is just 0.5 into t, which is given 0.10 millimeter. Okay, this is 10 to the power minus 5 into 10 to the power minus 5 meter. Okay, from here we can calculate the phase difference, which is 2 pi by lambda delta x. Okay, wavelength is given 600 nanometer, and so if you put everything, you will have 600, so 6 into 10 to the power minus 7 meters in terms of meters, and roughly if you calculate it, you will get 523.6 in terms of radians. Okay, now so this is the phase difference. Now due to this phase difference, how many fringes will shift on the screen? How do we calculate that? Any idea? So, okay, let me ask. So, what does this, okay, first of all, the fringe width beta, it is given like this, right? So, beta, if we keep this d and d constant, it is basically, dependent on the wavelength of the light, right? And we know that wavelength of the light lambda, right? So if we introduce something like which is changing the changing the changing the phase of the light, what we are doing is we are shifting this wave either in the positive or negative direction, basically, right? And that is what that's what will lead us to change the pattern on the screen, right? So for example, what I'm saying is, I mean, the formula is very simple. The shift that you will observe, number of shifts that you observe, is just this, okay, delta x divided by lambda, okay? But I'm trying to make you understand how this is the number of fringes that will shift. So to visualize this, you can look at the this picture of electromagnetic wave, okay? And so this is the wavelength, definition of wavelength. And when you introduce a glass plate, or by some means, when you change the phase, when you shift the phase of the light wave, okay, that will lead to the change in the number of fringes. Like if you were getting fringe number 3 here, so x3, due to this introduction of this glass plate, it will now change to something like 4 or 5, depends on the depends on the thickness of this slab and all, okay? So that's why this is the shift. So we have already calculated it, and we know the wavelength is also 10 to the minus 7, right? So you will roughly get 83 point something, but in whole numbers 83 fringes on an average will be shifted. Is that clear to everyone? So just remember, this is how you calculate the number of fringes that shift. So this happens everywhere. Like if you have Newton's ring experiment or Michelson interferometer that you will encounter later, everywhere this happens. Okay, let's go to the next problem. So this is the last problem for today, and this is a just a logical problem. So if you wish to perform a Young's double slit experiment with a wavelength with a light of wavelength 632.8 nanometer, okay, and obtain a fringe width of 2 millimeter on a screen at distance 2 meter, okay. What slit separation D is required? So this you can calculate easily, right? So this is, we have been doing. So this you can this you can calculate very easily using this formula, right? But the question asks, if the source is finite in width, okay, now this source, instead of a point source, it is of a finite width, such that the coherence is limited to 0.1 millimeter at the slits, okay. Or now due to this, the coherence, sorry, what I am saying is, yeah, now the coherence, this is basically coherence length given to you, 0.1 millimeter, okay. And it asks, will you get clear fringes, okay. So how do you calculate this? So first let's calculate D. So let's put everything, 332.8 into 10 to the power minus 9 into so D is 2 meters, okay. Beta is 2 millimeter, so 2 into 10 to the power minus 3. If you calculate it, you will get 0.6328 millimeters. So now this distance is 0.632, so 0.6 millimeter roughly, okay.
Sir, okay.
Yeah.
No, sir, means like cleared, doubt cleared, yes.
Okay. So this distance is 0.6 kilometer between the slits, and from this and this the source of light, it has a coherent length of 0.1 millimeter, okay. So you see here that the D is greater than L, right? It is greater than by factor of 6. So you can say greater than L. Right? And so the light source from S1 and S2 will not be coherent with each other, and your fringe pattern will have not good contrast, or it will be washed away, okay. So that is the basically concept of this problem, that so yeah, you have to see what is the coherence length, okay, of the sources. Is it okay? Is it clear to everyone? Yeah. Okay, thank you. So yeah, this was the last problem for today. Do you have any question or any doubts?
Sir, can you show the first 2 slides?
First 2 slides, okay. This is the first slide. And this is the second slide. Anyway, these slides will be uploaded on the website. You can access them. Do you have to
Sir,
ask?
I did not understand this time part. You told this concept.
Yeah, this one.
Can you tell this again? Yes, sir.
Yeah, okay. So yeah, what I was saying is basically here. So this you understand, right? The coherence thing. That none of, I mean, in reality, you don't have a source that is coherent. You will not have sinusoidal waves for infinite amount of time, right? Now, what happens is, if you are looking at time t, okay, in at point P here on the screen, okay, uh, the waves that there, the two waves that are reaching there, which is causing the interference, they have been emitted at one at t minus r1 by c. R1 is the distance from S1 to P, and the other one is emitted at t minus r2 by c. Okay. Now I am saying that if the difference in time, so the delta t, if you calculate, it will be basically r2 minus r1 by c, right? If the difference, this time difference is less than the this coherent time, so the coherent time is that time in which interval the wave is sinusoidal, okay, then you will have a good contrast of the fringes, like then they will interfere, and you will get constructive and destructive interference, and there will be a good contrast. Otherwise,
Yes.
yeah, otherwise, if that is not the case, if this time is greater than the coherent time, there will be no fixed phase relationship, right? So they will be out of phase and the fringe pattern will pass away. So that's what I was telling. And in this problem, it is similar concept but in a different perspective. Here it is said that this line source that you have, it is emitting waves, right? It is emitting waves, and these waves are coherent up to a very smaller distance, like this is the distance up to which they are coherent, okay. After that they are incoherent, and since our two slits are separated at a larger distance, right, the wavelets emitting from them will have different phase relationship, and they will not be coherent. So this is a different problem.
Okay, sir.
Okay. Anyone else? Okay, if there are no more questions, we can close this today's session, and let's meet next Saturday. Okay, thank you all for joining. Bye.
Thank you, sir.
Thank you.
Bye, sir.